right. Yeah. Hi, everyone. My name is Mohammed. I lead the compiler team at Essential. The reason we have a compiler team is we're building a language for writing smart contracts, but that's tailored for declarative chains. I guess you'll see why that's important in a second, but back to the stuff that Liesel talked about a little bit earlier. She was comparing imperative chains to declarative chains and imperative programming to declarative programming. I'll try to go very quickly over that again. I'm not going to spend a lot of time on it. So I have a few slides, and then I'm going to jump into some applications. I'm going to show how this classic counter example would look like on Essential, written in Pint, and then some Rust application around that, and then a token contract as well. So I think that's all we'll be able to cover today. But yeah, so yeah, declarative versus imperative. I mean, yeah, like imperative programming languages, the classic ones like Rust, C++, Java. You have algorithms, you have control flow. You have a lot of side effects. These are languages that are great, but they serve a very specific purpose. They are general purpose, but the style of coding in imperative languages encourages a certain type of thinking that's very algorithmic. Declarative languages, on the other hand, are more about outcomes, not so much about control flow, not so much about a step-by-step process. You're thinking in terms of the logic of the application you're building, and not so much how it's executed on the CPU in terms of a sequence of instructions. So yeah, what versus how is kind of how you want to think about the difference between these two programming paradigms. Constraint programming in particular is one example of declarative programming. Languages like Prolog is considered like a constraint programming language. There are others, but the idea is you have constraints on some variables, and the end goal is to say, give me a solution such that all these constraints are satisfied. And a solution in this case is an assignment of these variables. That's pretty much it. In a very simple high school term, or elementary school, I guess, you could say, give me x and y such that x times y is 100, and x plus y is 25. And someone could say, okay, I know the answer, it's 20 and 5. And I could go back up there and plug in the values, and I verify that this is actually correct. When I wrote those equations, at no point did I say, this is how you get to x and y. I never wrote steps to get you to x and y. I just gave you what I want. And someone else, potentially with their own algorithms, figured out that x and y are 20 and 5 in this case. So, mirroring that to a blockchain application, x times y equals 20 or 100, and x plus y is 25. Those are constraints. And this is a solution where a solver would propose that. So, yeah, what does it have to do with us specifically? Thinking about languages like Solidity, based on imperative programming, Solidity is made to be kind of a Turing-complete programming language that lets you do whatever you want effectively on the blockchain. And that was a very nice property, but the problem is we ended up in a situation where doing anything fairly complicated becomes very expensive. So, turning it down and thinking about what smart contracts really are, or what their purpose is, at the end of the day, they're meant to enforce a state transition. They're meant to enforce certain rules on how the state should go from A to B. And again, Liesel covered that in depth earlier, so I won't talk too much about that. But yeah, so this is kind of why we're building this. Pint is just, which is the language we're building, is a new way of writing smart contracts that is just completely constraint-based. All you write in your contract is constraints, which you can think of as asserts or anything similar to that. And You never at any point say, this is how you go from state A to state B. You never have like complicated algorithms in there. We leave all that stuff for off-chain code, which can be written by some other language like C++, or Rust, or Java. And these languages are much better at that than any smart contract language we're going to be able to build, because they've been around for so long. They're not on the CPU. They're optimized. We're happy with them. There is no need to reinvent the wheel and like run everything on the blockchain. Like that was never the goal of like the EVM. The goal was always like guaranteeing certain state transitions. So yeah, I mean, this is what some Pint code will look at. We're going to look at this in just a little bit. But a contract in Pint is storage, which is common for most programming or smart contract programming languages. You just have storage that like storage variables. And then you have a set of predicates, which you can think of them as a set of methods, but really there are no methods here because nothing is called. And I will try to emphasize that concept later on quite a bit because it's very important. Predicates are just sequence of constraints that hopefully all of them evaluate to true if the solution is valid, and otherwise the predicate will fail. And then the state transition proposed will not be accepted. A predicate itself is a set of variables and a set of constraints. And that's really all of what the language is. That's it. So, I mean, let's just jump in right away. I'm going to do a quick demo now, and we'll see how far we can go. I have everything at that link, which I will put that demo back up at the end, or this slide back up at the end. I do have the slide deck there, and I do have the two applications we're going to talk about, both the contract code and the Rust code. Okay, so the first application we're just going to look at is the counter, which that's always the first application you look at when you learn a smart contract language. Very simple. This is a counter project which just has a single file. It has a pint.toml file, which is similar to Rust's cargo.toml file, which has information on how to build this stuff. But let's focus on the contract itself. We start by declaring the storage. In this case, we just have a single storage variable called counter, type int. Very simple. That's fairly common. Nothing really new here. Then we jump into the predicate that we're calling increment. We could have other predicates similar to it later on if we want, but for the counter example specifically, that's all we need. The predicate increment has effectively a single constraint, but split into two separate constraints because of the if-else, and we'll talk about that in a bit. But the first line on line 7, I first get an instance of my counter. So this is kind of a variable of type int that I'm also calling counter. It's a local variable. It's state, so it indicates that this refers to a storage variable. And I get access to it by saying storage colon counter. So it's as if the storage block up there has its own namespace. And then I'm going to say if counter is nil, and this tells me that has the counter been set before or not. So counter equals nil, if that is true, then the counter has never been set before. So this is the equivalent of saying it hasn't been initialized. So in storage, this means that the storage slot where the counter lives has nothing in it, right? In the EVM, there is no such concept because everything is initialized to 0, technically. If you read any storage variable or any storage key, you're just going to get 0 back. In Essential, that's not the case. where you can start with an empty slot. And so you check if the counter is nil, and if the counter is nil, then you just set it to 1. And so there's an interesting syntax here on line 10 that says constraint counter prime equals 1. So obviously the keyword constraint kind of is self-explanatory. The prime notation might look a bit weird to you, but what we mean by that is it is the next value of the counter. So we've been talking about going from state A to state B, and that's all what declarative chains care about and declarative programming languages care about. This is B, right? Like A is the counter and B is counter prime. We're going from counter to counter prime. This is the goal of this predicate. And if this predicate is ever satisfied, the new value of the counter prime, should be equals to 1 in the case where the counter hasn't been set before. That's basically what the first if block is saying. And the second block is saying, if it has been set before, if it's not nil, right, then I'm just going to increment it. I'm going to say the new value of the counter must be equals, hence the equal sign. It's not an assignment, it's a Boolean expression. Must be equal to the old value of counter plus 1. Now you may be wondering, why do we have like prime and why there's no assignment? That's because these are constraints. They're not instructions, right? There is nothing that's getting executed here. Generally, assignment in programming languages imply control flow. You imply that there's a sequence of things happening. And at some point, you have X, and then in the next line, you're going to say X equals to X plus 1. So the order in which you arrive to that statement matters. In here, this is irrelevant. Like the order in which you declare your constraints is not important because they're just constraints. There is no control flow. Like when the compiler takes this piece of code and compile it down to bytecode, I'm not getting something that gets executed and gets me back the new value of counter. I'm getting something that accepts solutions, which we'll talk about in a bit, and then verifies whether these constraints are valid. And each constraint that I'm going to write, it's just verified entirely independently of the other, right? And that's a very important property because it implies complete parallelization of the validation process. Because every single constraint you can write in here, in the ifs, outside the ifs, everything that's here can be completely validated in parallel. So this is it. This is the counter example. I don't need like an initialization predicate because the if on line 9 kind of takes care of that. So just to quickly show like how I would interact with this predicate from like an application. This is Rust. I mean, there could be other frameworks in the future that would allow us to interact with contracts, and they will be. For the time being, we have a way to interact with contracts from Rust because the VM and the server and all the stuff we built is in Rust. So, put simply, if you know Rust, that's good. If you don't, that's fine. I'll just kind of describe this at a high level and should hopefully be fairly clear. So I just have an application object that in it, I just have the client, which is the client that I'm going to initialize later on in my tests. And the client has the VM in it, of course, and it will allow me to submit solutions, deploy contracts, and interact with them. And I also have an increment predicate address. Predicates have addresses similar to contracts. So contracts have addresses, predicate have addresses. So I'm going to keep track of that address. And I'm going to show how to get that address in the tests. And so I do have a new function that creates an instance of this whole app. And then I'm going to come to the increment function. So this is the most important part here. So on line 32, I'm going to say, give me the current value of the counter. So what this does is, since counter lives in storage, this is going to query the state of the blockchain to give me that value. So I'm not going to show how that's implemented. It's implemented at the bottom. You can look it up later. But effectively, it's going to figure out from the contract itself where that counter lives, and then it will get its current value, and it will increment it by 1. That's pretty much it. And as the application developer, I know that's going to be the solution, right? This is the process of solving effectively. So the increment function here is coming up with the solution so that when I submit that solution to the counter contract, the predicate itself, i.e. all of its constraints, will be satisfied. So that's very important. So I'm going to create a solution object which has a bunch of things. The only thing that matters to us for this particular example, the predicate to solve, which I'm going to say which predicate I'm solving in this case. So I'm going to pass in the address of the predicate. And on line 38, I have the state mutations. So what I'm going to say here, I'm going to mutate the counter, and I'm going to set it to new count, because the new count is basically the old count plus 1. So that's my solution. So if you think, let's say my counter was 0 before, right? Then my new count is going to be 1. Then when I build this solution, I'm going to set the value of the counter to 1. And then a validator will go back, take that solution, and update the value of counter to 1, which means on line, let's say line 14, if the counter value was 0 before, then constraint 14 will be satisfied because counter was not nil, right? It was 0 before, hasn't been nil, then I'm going to jump to the constraint on line 14, and counter prime is 1, equals 0, the old value plus 1. So that constraint is satisfied, which is basically the only constraint that matters in this case. So the state update will be accepted. And yeah, that's pretty much it. So I crafted the solution, and I'm going to submit it to the client on line 41. And this is my Rust application that is able to interact with the contract. Again, it's very important to keep in mind that really nothing here is getting called, right? Again, there is no calls, there are no returns, there's no execution of any sorts. This is, you can think of this as a circuit that you just has inputs, which in this case are the state transitions, and has a single output, which is a Boolean, true or false, and that's pretty much it. This circuit does not operate until someone gives it inputs as a solution. So unlike, if you were writing this in Solidity, you're going to have an increment method which you have to call. And this terminology is very different and does not exist for us. Now, this may seem a little bit silly for a counter example, but we talked about parallelization. We talked about not having to think about execution and algorithms and all of these things. Just think about how we kind of figured out the new value. The app did, not the predicate. Like the new counter value was kind of figured out by the application itself. So in a more complex example, the application will have some complex algorithm potentially to find the solution. And that's fine. What we're saying is doing that in the smart contract code is not the right way to do it, because as we've learned, smart contracts, if you're going to run things or heavy things on the blockchain, it's going to be costly, it's going to be expensive, it's going to have bugs, it's going to have security flaws, and you're going to spend month, gas golfing and trying to figure out how to write your contract in the best way, and none of that matters here. In fact, the simpler your contract, in here, the better. You're never going to have people sitting down and trying to optimize this stuff down to like, oh, I'm going to save, 5 gas here and, make the bytecode smaller or whatever. Like this stuff is completely irrelevant because it's just constraints. So feel free to interrupt me, by the way. You can jump into the token contract quickly, or we can take questions. Okay. Yeah, the token contract is going to be a bit more interesting. Hopefully, a lot of you have seen what an ERC20 token contract looks like in Solidity. This is kind of just a distilled version of what a token contract could look like on the essential chain written in Pint. Now, this is not complete. It's missing a few things, but I've distilled it down to what you see here for simplicity. And at the end, the link I'm going to link to has a link to our repository that has a bunch of applications. These ones are complete. For the time being, this is kind of a introductory way to think about basic things like decision variables and authentication. So as with most token contracts, probably all of them, you're going to start with a storage block that has a balance or balances, a storage map that's called balances that maps addresses to values. Addresses for us are B256, which is a way to represent a hash or a 256-bit number. An int is just, that's our int, I've seen it before. And on line 7, we have a const minter, which is the address of the account that's allowed to mint this token. We hard-coded this here. It doesn't need to be hard-coded. It could be in storage and changed later. You could do whatever you want. For simplicity, it's hard-coded here. We define a type. This is a type alias, which you may be familiar with from other languages like Rust. It's just a signature type. And it so happens that this particular signature has effectively 9 words or 9 integers. And so it's B256, which is 4 words, another 4 words, and then an int. A word in the essential VM is 64 bits, by the way. And that matches what an int is. So the first predicate is mint. Of course, the goal of this predicate is to create new tokens and send them to a particular address, right? We're not transferring anything from one account to another. We're creating tokens from out of thin air. So for that, we need 3 decision variables. Now, the concept of a decision variable we have not seen in the previous example, but it starts with the letter or the keyword var. And we have a var2, which is the receiver, which is an address. This is where we're sending the tokens. We have a var amount, which is how much we're minting. It is an int. We have a signature, which we will show why this is needed later on. On line 22, kind of like we did with the counter, we have to read the state. Why? Because we have to get the current balance of the receiver so that we're able to increment it, right? Because that's what we want to do. We want to read the current value and then say the new value is going to have to be incremented by amount. So on line 25, we say, So on line 22, we access balances of 2, right? Which is kind of like a map access. That's the usual syntax. And on line 25, we say the address of the receiver has to match minter. This confirms that the person or the account that's minting is the right one. so that no one else can actually mint. And then on line 27, we're saying, if the previous balance was nil, then the new balance should be amount. And otherwise, the new balance should be incremented by amount, which is, again, very simple to the counter example. We've seen this pattern before. So this logic should hopefully be clear. And that's it. That's the mint predicate, right? Like, if you think about it, that's, think about it in terms of how do I get from nothing to certain amount of tokens in the possession of some account. That's how you'd express all of that mathematically, right? Again, no execution, no order. Like, you can do all of these things in any order you want. This is more like a circuit than a sequence of instructions. Now, on line 36, things get a bit hairy, but this is a security thing. Naturally, like, you're used to this in Solidity, where you write message.sender, which guarantees that the person who is calling the contract is the one that that you have a reference to, so that you can access their own balance. There is no sender per se for us, which is why you have to submit signatures for everything you're doing. Now, a signature is basically, you take the hash of the rest of the variables that you're submitting, and then I'm going to show that macro at the end. And then you make sure that when you recover that signature, then the key matches the key that I'm dealing with here. So this validate signatures syntax here is a macro. So it's another concept in this language that we haven't seen yet. A macro is just a macro. You have seen macros from Rust or other languages, similar to functions, a bit more versatile because macros, at least for us, can do anything. You can pass in any form of, like, you can pass in a plus sign as an argument if you want. You can do whatever you want with them. They're very, very flexible. In this case, this particular macro takes 3 parameters, and they're signature, key, and data. And you make sure that the hash of the data, and when you recover the hash of the data given a signature, and you hash that back, you get back the key. Now, you don't have to understand how that works, but if you're familiar with the different signature schemes, you should hopefully be fairly clear. Maurice? You mean calling the macro up here? Yeah, you can do this anywhere you want. Yeah, you can put that constraint at the beginning. Doesn't matter, right? The constraint really is just, in this case, it takes a bunch of variables as inputs, and then its output is either true or false. And so you can put it anywhere you want. Again, the reason why I'm saying this is, like, the value of balance is never changed in this code. The value of balance prime is never changed. There are no temporaries. It's just data that's being provided for us from the solver, right? So this piece of code serves as constraints that the solver will look at to produce solutions. And they also serve as bytecode that you submit the solution to as inputs, and you produce a true or false out of it to check whether, and that's what the validators will do, to check whether to accept the state update or not. Simon? On line 22? Yes. Correct. Correct. So nothing's actually being read per se. Just like Simon was saying, it's just we're saying the balance here. This particular variable represents, if you want, that's a better word, represents the value at this particular storage location, right? And then I'm going to reason about that value later on. I'm going to reason about its own value or its current value and its future value via the prime operator. Yeah. Correct. Yeah, so that state mutations that we showed in the app, and I'm going to show that again. That state mutation is what the solver will propose. It's the new value of balance. They don't have to submit the old value because the old value is available on the chain. They just have to submit the new value. So yeah, I mean, that's pretty much it. What I've done so far, I've made sure that the receiver or the account that's receiving the tokens and the account that's minting the tokens are the same and they're minter. This is a situation where, or this is a predicate where the minter sends the stuff or the tokens to themselves, and then they proceed to do whatever they want with them. We've made sure that the new value of balance is incremented accordingly by amount, right? And then we made sure that we've authenticated the account that submitted this solution. Or we've authenticated the account on whose behalf the solver submitted a solution, right? And we did that by signing, because signing is a way to make sure that the key that we're trying to update matches the person on the other side who actually did the signing. So strictly speaking, there are two more things I need to do here. I'm not going to dig too deep into them. One of them is handling the nonce to avoid double spend. There's no nonce per se embedded in the protocol like Ethereum. So I technically need to keep track of the nonce in the storage block separately, and each account will have its own nonce, and I'm going to increment the nonce every time this particular predicate is called. That's one thing. And the other thing is making sure only very specific storage locations are allowed to be updated in this predicate. This is a security concern. You don't want solvers to be able to submit random state updates that have not been constrained here, right? It's a bit of a subtle point, but there's nothing here that restricts state from someone else or from state that is not constrained in this particular predicate to be changed. So you need to make sure there's extra statements in there that make sure that that's the case. So yeah, like the nonce, the the signature verification, and the number of keys or the keys that are allowed to be modified in state are not part of the core logic of the predicate, but they're there for security purposes. We could go over the transfer intent as well, or the transfer predicate. Fairly similar. There shouldn't be any new concepts here. We have an extra decision variable called from, because we're transferring from somewhere. And yeah, we have a signature, the amount, the to, and then the rest is fairly simple. We have two state variables in this case that are the balance of the from, the sender, and the value of the receiver. We make sure that the balance of the sender is at least amount. You want to make sure that they have at least this many tokens, and then you update their balance. You decrement it by amount, and that's constraint 63 on line 63. And then at the end, you make sure to update the balance of the receiver. And then you validate the signature to make sure that the receiver is who they claim they are. And that's pretty much it. That's a transfer predicate. Yeah. I don't have other predicates here. You could add a burn predicate, fairly simple, in just the opposite way of mint, very easy. And yeah, that's a token contract. We're out of time, but if you guys have any questions or you want to chat about this later, please let me know. They get this whole contract is deployed. Yeah. So both contracts would be deployed. Um, oh, you mean approval is part of the same contract? Yeah. So you could submit solutions that solves two separate predicates and two separate contracts. That's actually very important. You can think of the swap example, like if you have a exchange contract, the exchange contract has to reason about a token contract, right? Because that's where the tokens actually live. And so any solution you submit to a DEX contract has to have components that reason about the token contract as well, and potentially other things. So this is actually a very important point. Mm-hmm. Not at the moment. This is, well, I'm going to say no. Yeah. Yeah. Yeah, that's it's a hard question. I don't have a very good answer to you right now. We could have a chat about that. This is not something we've thought about too much just yet. Yeah. Yes. That's another very good point. I'll show you later, and actually the links I'm going to show. Let me just put up this slide again so you guys can have access to the link. But yeah, I'll show you code in a bit. That's a very good point. And that's very important because there are no accessors like in Solidity, but storage is public. So one contract can directly read storage from another one, and we have a very specific syntax to do that. Well, thank you, everyone.